Hi there, my name is Dmitry and I welcome you on my technical channel. We continue our workshops about Zynq7000 SoC from Xilinx and RTZ7 board. Today we are going to look at a project capable of generating a video signal, which is understood by most of modern monitors. I'm talking about HDMI standard, which became a common interface nowadays. It can deliver exceptional video and audio quality, but at the same time, it puts a lot of pressure onto hardware which generates video. This is due to relatively tight timing requirements of the video signal. Those requirements are heavily dependent on the chosen resolution, color depth, and refresh rate. But in any case, this is not an easy task even for such a high-performance multi-core SoC, which we are going to use today. Even ARM core running at 600 MHz is not going to tackle the job. This is why we have to leverage the use of FPGA or PL side to achieve our end result. Today, we will be looking at a project which uses both PS and PL sides, or to put it differently, a project which has logic on ARM core and on FPGA side. As a baseline, I took a project originally designed by the company called Digilent. The project is readily available on GitHub and it is called HDMI out demo. I converted it to my own version of Vivado, which is still 2017.3. I have already created a Vivado project, synthesized and built it, and then I have created an SDK project based on the HDF file that was generated by Vivado, and then successfully compiled and built it. Let's open it in SDK IDE and try to run it. You can see there is no errors, and the run configuration is already set because I run it at least once. Now we will need to start a terminal application. Now we need to connect HDMI cable to HDMI out connector. So instead of my camera looking at the board, I connected RTZ7 output. So theoretically speaking, we should see something as soon as we run the application. Let's run it. Our application started. Let's switch the camera. And yes, we can see a nice colorful pattern. What can we do with this? Change display resolution. Let's try to press 1. Let's choose 1280 by 1024. Yeah, seems to be working. Invert current frame colors. Yeah, seems to be. Invert seamlessly. Well, it does stuff. Let's go back to the original resolution. Blank frame 7. Well, not so blank. Print blended test pattern to display frame buffer. Well, it obviously works. Let's have a look at the details of this demo in order to understand it a little bit better and see what we can change and improve in it. Now, let's go back to Vivado and have a look at the BD board design and try to understand the purpose of each component. First of all, what we can see. We can see already known component processing system, which is an integral part of each project. And in essence, it represents a set of ARM cores plus hardware interfaces, which are not part of the FPGA fabric. Processing system is connected with FPGA through several interfaces. In this case, it is HP, high-speed port, AXI, high-speed port. What else we can understand from it? There is a component on FPGA side, AXI interconnect. Which has one port. And we can see that there is a second AXI interconnect component. And it is connected to different interface, AXI GPIO. Now, we can see that there is a processor system reset directly connected to AXI interconnect. And then we also see that there is a second instance of processor system reset. Why do we need two of them? Well, because the reset line of the processor system reset is connected to the AXI-MEM interconnect, and the same in this case. It means that each AXI interconnect component requires its own reset. A component called concat is connected into IRQ bus, and intuitively it is also logical because we can see that somehow it combines several IRQ lines IRQ into IRQ bus. Well, at least that level of understanding is enough for now. So we managed to understand the purpose of at least half of the components on the BD design. We can understand that AXI interconnect plays a significant role in connecting the PS system with memory, and we can see it goes directly into AXI VDMI, Video Direct Memory Access. It's a separate component again. What else we can see? We see that the output of the AXI VDMA is connected to the input of subset converter. It looks a little bit strange, but in essence, what it does defines some kind of rules how to manipulate with the T data lines, as we can see. So simply speaking, it remaps the lines of T data bus, and this is all we need to know for now. What else we can see? We can see that AXI dynamic clock generator again is controlled by AXI interconnect, just the way as the AXI VDMA is controlled, AXI light interface. It means that we can access internal registers of each component through that AXI light interface, and then we can reconfigure the mode of each component. This is also logical on a high level. As you can see, every single component is controlled by AXI light interface. So the AXI dynamic clock, it has two outputs pretty much. One input, which is reference clock, and two outputs. One is called pixel clock, and the second one pixel clock multiplied by 5. Which is also called serial clock. If we look at the description of HDMI interface, we can quickly realize that serial clock is 5 times faster than pixel clock, just because the HDMI interface is in essence a serial interface. So whatever data we have on a parallel bus, which is RGB, you can see 24 bits of data clocked by pixel clock. So that bus, that parallel portion of data, gets converted into serial sequence, which is clocked by a serial clock. And this is the essence of HDMI interface. And it goes straight into TMDS bus. What else can we see? We can see that the video data, video in, again we can see same data bus, 24 bits, which represents 3 colors, 8 bits per color. So the data bus is somehow mixed with timings, and timings is basically described by just several signals: active video out, H blank out, H sync out, V blank out, V sync out. At this point we probably should have a look a little bit at the video timings. This picture represents a screen with area painted blue, representing visible pixels. Apart from it, we can see that there are front and back vertical porches and front and back horizontal porches. So we can see that there are specific values for each parameter for a specific resolution. So which signals we use to define those special areas? Here is a little bit better picture that represents active area in blue, and the special fields are defined by H-Zynq signal and HDE, and V-Zynq signal and VDE. And the combination of HDE and VDE represents data enable. So whenever data is enabled, whenever data enable is high, it means that we are going through an active pixel area. Or it will be one of those porches otherwise. The beginning of each porch, be it horizontal or vertical, is denoted by Zynq signals. So in total, what we really need for our video signal is vertical sync, horizontal sync, data enable, normally and usually it is combined. Two signals are combined into one, data active, and the data bus to represent information about pixel colors. And this is what we see: active video out, H blank out, H sync out. Yes, the active video out is a combination of H blank and V blank. H sync out and V sync out, we already understood that those are the beginnings of those special areas. So we can see that timing signals and the data that represents colors for each pixel, they get mixed and go straight into the video encoder, which converts signals into the serial data stream, and then it goes into HDMI. As for the XGPIO, let's not look at it at the moment. Let's try to understand what we can do and how we can learn from this. Let's have a look at the XE VDMI block and try to understand whether it is capable of doing anything we would like it to be doing or not. And by the look of things, there are not so many options, and the pixel data is organized in a linear way. Let's say we would like to implement a video controller of a computer from the 80s, which was called the ZX Spectrum. It used to have an exotic organization of video memory, which contained of two blocks of data. First one was bitmap data, and the second one was color attribute data. So in that sense, it was non-linear, and if we ever wanted to implement this video controller, we wouldn't be able to use a standard AXI VDMI block for it. So let's set a goal and implement a video controller for the well-known computer ZX Spectrum, but let's do it in two steps. The first step, we would like to start feeling a little bit more comfortable about this design, and first of all we would like to get rid of AXI VDMI block and instead connect the input to the subset converter to our own module which for now is not going to use memory, and it will be generating a test pattern of some kind. That should simplify our steps towards our goal. First of all, we would like to disconnect this block and instead make this interface external. Now, let's rename it. We will also need clock and reset. So let's create a new port, reset, output, reset, and one more port, output, clock. Now, going back to reset net, we need to make connection, reset, and the clock for axis stream to memory to stream, this is the one. Make connection, and we can see our axis clock connected. Regenerate layout, save. Now, what I also did, I added new signals to the wrapper, and to see the difference in a better way, more convenient way, we can compare all the new file. As you can see, we added clock, reset, and then the memory stream bus: tdata, tready, tuser, tvalid, tkeep, tlast. So this is this one. If we go to signals, no, tdata, tkeep, tlast, tready, tuser, tvalid. So this is part of our board design. Those signals are external to the board design. Now, what I also did, I created a new module, which is called test pattern generator top, which I will talk about in a second. Declared or defined a new set of new signals, then connected our board design to those signals, and eventually instantiated test pattern generator and connected its ports, connected its signal to our BD in essence. Now, what I also need to do, I need to add a new file to our project. Vivado sources test pattern generator. Let's have a look at it. Test pattern generator. So it contains already exposed, signals from the BD, which includes reset, clock, and the stream interface. What we also have, we have a state machine, very simple state machine, which contains 3 states: idle, streaming, and end of line. We defined a few constants. We're going to use in this example fixed resolution, 640 by 480 pixels. We also defined the maximum value for color for the one of the colors, be it R, G, or B, and the minimum value will correspond to black in essence. And a few signals we also defined. This is the actual state, which has a type of TSM video stream, and a set of signals and a few counters. Upon reset, we initialize signals to known state, initial state, and this is the actual state machine. Relatively simple. What it does, it waits for the interface to become ready. We initialize the counters and the initial states of the signals, and then simply transition into streaming state. In streaming state, we assign maximum intensity to blue component and minimum intensity to red and green. We also have a logic that increments vertical and horizontal counters, and we remain in this state while the stream is ready. And until we finish the full frame. Once the full frame is done, we transition into end of line, if you like. And this is the end of our frame. The outputs are assigned to the values of our signals. This is how we assemble the full 24-bit data bus, which is comprised of red, green, and blue, obviously. So let's try to synthesize this project. In essence, what we expect to see, it should be screen filled with blue color, as you can see. The only component which is blue is set to maximum intensity. Everything else is supposed to be black. Let's run synthesis. run implementation, and at the same time let's start the SDK again. Implementation has finished. Generate bitstream. Bitstream is ready. Let's export hardware file. HDMI out demo. Yes. Go back to SDK. It should detect the change in HDF file. Yes. Regenerate it. Okay, let's try to run it. Switch. And yes, as we can see, the whole screen is filled with a nice blue color. So in essence, we are generating a video signal without use of XE VDMA. As you can see, the output of it, access MM2S, memory to stream, is simply disconnected. Instead, we are injecting a signal which is generated by our test pattern generator. Now, what we can improve and what we can make look a little bit better. Let's say instead of a blue screen, let's generate a 3 bars RGB stretching across the whole screen. The changes are going to be minimal. We will need to define vertical positions for scan lines where colors are going to be changed. So we start with the red color. As soon as we reach 1/3 of the screen, we switch to green, and then as soon as we reach 2/3 of the screen, we're going to produce blue color. Let's copy those changes to our project and rebuild it. Save. Run synthesis. Run implementation. Generate bitstream. Done. Export hardware. application. And see what happens. And this is exactly what we wanted to achieve. So now we can generate colorful test pattern. That's all what we wanted to do. Next time we are going to implement our first video DMA module capable of fetching pixel data from memory and generating a monochrome picture on HDMI output. Until then, stay tuned. See you later.